Now, just like we did with resistors, we can also find capacitances for networks of capacitors. If we take this example here, we have 4 capacitors in a circuit, and they're in a combination of series and parallel. We can figure out what's going on. We can see that C2 and C3 are in parallel with one another, while C1 and C4 are in series. C1 is in series with C2 and the combination of C2 and 3, and then C4 is in series with that. So our total equivalent first off, our equivalent capacitance for 2 and 3, I call that C23, is going to be C2 plus C3. And then the rest of them are in series, which means they're adding with the inverse style. So 1 over the equivalent capacitance would be 1 over C1 plus 1 over C23 plus 1 over C4. All right. So we can figure this out. C23 is C2 plus C3. 19 plus 25 is 44 microfarads. So then 1 over our equivalent capacitance for the entire circuit is 1 over 15 plus 1 over 44 plus 1 over 22 times 10 to the 6th, because those would each be times 10 to the minus 6th in the denominator. And if I punch that into my calculator, 1 over 15 plus 1 over... Can you actually see my calculator? Yeah, kind of. Plus 1 over 44 plus 1 over 22 times 10 to the 6th. Let me take 1 over that and get that our equivalent capacitance is 7.4, etc., about 7.4 microfarads. And then we could figure out the total charge, because that's equal to C over E, Q over, yeah. The EMF is equal to the total charge over the equivalent capacitance. So then we have 14 equals that total charge over 7.4 times 10 to the minus 6. So then the total charge is just that 7.4 times 10 to the minus 6 times 14, which is 1.03, etc., times 10 to the minus 4th coulombs. And we could break this down and figure out what is on each capacitor as well. So since C1, C2, 3, and C4 are in series, it means that C1 and C4 have the same charge on them, and C2 and C3 together have the same charge on them. So that means that we can say, so since these C1, this pair, and the last one are all in series, they have the same charge on them. So we can say that the Q1 plus Q23 plus Q4 is equal to the total charge, and each of these are equal to each other as well. So we just divide the total charge by 3, and that'll get us Q1, Q4, and Q23, which is 3.46 times 10 to the minus 5th coulombs. All right, so that's the total charge, and then we could figure out the charge on each of C2 and C3 because we know the voltage across them is the same, which means that the Q2 over C2 has to equal Q3 over C3, and we know that Q2 plus Q3 has to be that 3.46 times 10 to the minus 5th. So we've got a bit of a system here. We can say Q2 plus, if we substitute in, Q3 would be equal to Q2 times C3 over C2 times C3 over C2, and then figure out what charge is on each of those. I'm running out of space here, and I have another circuit down below, but we can go ahead and punch this in anyway. So that we know. Yeah, so we've got, if we factor this out, this is Q2 times 1 plus C3 over C2. So then Q2, we just divide that charge by 1 plus C3, which is 25, C2 is 19, and so we know that Q2 is 1.49 times 10 to the minus fifth coulombs, and then we can subtract that from the original, from the 3.46, which we know they both must have, to get that the other one has 1.96 times 10 to the minus fifth coulombs. So we can figure out what charge is on each of those capacitors. We can also do more complicated networks. This is more complicated, so I'm not actually going to calculate the numbers for it, but we can figure out how we're going to break this down. Well, first off, we can see that C1 is in series with the rest of the circuit. Everything has to go through C1 before it starts branching off. All right. So we can go C1. We know our equivalent capacitance is going to be C1 plus C2, 3, 4, 5, 6. All right. From there, we can. Oh, that's nasty. Oh, hold on. We can't have this here. If you have a wire that bypasses any circuit elements, it's called a short circuit, and that would prevent the current would just naturally flow through this wire because there's no resistance. There's nothing that prevents it from flowing through that wire, and it would just bypass everything else in the circuit, and nothing would actually happen to the other capacitors. So we can't do that. But if we look here, we can see that there's a branch here, which means that C2 is in parallel with the rest of everything. So C2, 3, 4, 5, 6 is, oh shoot, I apologize. C1 is in series with the rest of the circuit, which means that they add reciprocally. C2 is in parallel with this, so C2 plus C3, 4, 5, 6 is equal to that equivalent of all of them combined. And then the rest of the circuit is just like our circuit was up at the top here, where C1 was in series with the parallel combination of 2 and 3 and 4. So C3 is in series with the parallel combination of 4 and 5 and 6. So our C3, 4, 5, 6, 1 over our C3, 4, 5, 6 is equal to 1 over C3 plus 1 over C4, 5 plus 1 over C6. And then our C4, 5, because they're in parallel, is just the sum of those two. So, we'd chain our way all the way back through, and then we could figure out the equivalent resistance of the circuit that way. So we can figure out stuff for networks of capacitors, just like we did with resistors. You could also do something like I could ask you a question about finding the energy stored. And actually, let's do that. So let's say this is a 12-volt battery. Let's say this is, we'll just make this simple, 11 microfarads, 12 microfarads. I'm not going to stop and think about these. This is 13 microfarads. C4 is 14 microfarads. C5, C6, oh, did I not make this? Oh, I did make a C5. And this is 15 microfarads. Okay. So if I ask you a question, I say find the energy stored in the circuit. Okay. Well, we know that the energy stored in a capacitor can be written in several different ways. The one that I always remember, for whatever reason, is the half CV squared. I guess you could go half QV as well, but this is probably the easiest because we already have the EMF, and this C in this case would just be the equivalent capacitance. So we need to find that equivalent capacitance, which is going to be a bit of a pain, but we can do it. C4, 5 is just the sum of C4 plus C5, so that's going to be 13 plus 14, 27 microfarads. That's C4, 5. Then 1 over C3, 4, 5, 6 is equal to 1 over C3, which is 12 microfarads, plus C4, 5, 27, plus C6, which is 15 times 10 to the 6th. And that gets us the equivalent capacitance of 3, 4, 5, and 6, 1 over 12 plus 1 over 27 plus 1 over 15 times 10 to the 6th, 1 over. So we get that C3456 is 5.34 times 10 to the minus 6 farads, or 5.34 microfarads. Then we can see that 3C2345 is C2, which I did not label. We'll call it 16 microfarads. Is 16 plus 5.34, which is what? Oh, shoot. I added 16 and not 16 times 10 to the minus 6, which is 2.13, times 10 to the minus 5th, actually. So that's 21 microfarads now. And finally, 1 over CEQ is equal to 1 over C1, which is 11, plus 1 over the combination of the rest of them, the 21.3 times 10 to the minus, or times 10 to the 6th. So our total equivalent capacitance is, I'll store this, 1 over 11 e negative 6 plus 1 over, answer 1 over that, is 7.26 times 10 to the minus 6 farads, and therefore our total energy stored in the circuit is 1/2 times 7.26 times 10 to the minus 6 times V squared, which is just 12. And if we punch that in, we get 5.226, call it 5.23 times 10 to the minus 4th joules being stored in the whole circuit. And we could break that down in kind of the same manner we did up here. We could break that down to figure out how much of that energy is stored on each capacitor if we find the charge or the voltage drop across each capacitor, just like we did up here. But I'm not going to do that for this circuit.